KSP is one of the easiest equilibrium problem types to solve. There's a little bit of algebra involved, but conceptually it's very easy. You're looking at, in something that's considered to be insoluble, just how many ions are actually dissolved with any insoluble compound. There's still probably some degree of solubility. Your solubility product constant, or KSP, you have no KSP values for soluble salts because they're considered to be 100% ionized. A solution has to be saturated in order to be in equilibrium. Your barium sulfate ionizing to barium 2+ and sulfate 2- has a KSP expression written as follows. And the KSP being 1.1 times 10 to the -10 indicates only a very tiny amount of the solid will form ions. Write the dissociation equation and KSP for calcium phosphate. So write the dissociation, make sure you're balancing the ions, and when you write the KSP expression, you'll need to cube and square those values. Make sure you know the difference between solubility and solubility product constant. Solubility is the molarity, the amount that dissolves per liter. Solubility product is KSP. To determine KSP, write the expression, somehow determine the concentration of each ion, plug it in, and solve. So here's a nice example. They tell you the silver ion concentration. From that, you know the chloride ion concentration since it's a 1-to-1 ratio. So at equilibrium, you have 1.34 times 10 to the -5 molar of each of those species. Put it into the KSP expression and solve for KSP. Here's another similar problem. This time, they give you the concentration of the magnesium ion. And looking at the equation, you can see that you would have twice that concentration of fluoride ion. So put in your magnesium ion, double it to get the fluoride ion. Put it into the KSP expression, so not only have you doubled the fluoride ion, you also now must square that value to get the KSP. Bismuth sulfide, they're giving you the solubility of the solid, so even though you will not use that mathematically, that will tell you the concentration of the ions. So you'll have double that concentration of bismuth 3+ ion and triple that for the sulfide ion. Once you get those molarities, you then need to put it into the KSP expression, so you'll have to square and cube those values to get the KSP. Molar solubility calculations are like any ice calculation. You're actually finding the molar solubility. So you'll write the expression, find the number of ions in terms of X, solve for X, and put it into the expression. So they give you the KSP for this reaction. You write your equation, put your KSP expression. You start off with 0 calcium and 0 fluoride ions. Notice 2X is the increase in the fluoride ion. When you put the x's into the equilibrium expression, you get 4x cubed. Solving for x gives you the molarity of the calcium ion. The fluoride ion would be double that concentration. KSP for calcium fluoride, again, your x is 4 times 10 to the -4, giving you, if you asked, or if they asked for the answer in grams, you would turn the moles of calcium fluoride into grams of calcium fluoride that dissolves per liter. Ksp for copper 2 iodate, and they want to know the concentration of the iodate ion at equilibrium. Write the equation, do your typical ice, draw straight lines down through your solid copper iodate, since that's not going to be in your mathematical expression. Solids are not in your equilibrium expression. That gives you x times 2x squared gives you 4x cubed. Solving for x gives you the copper ion, the iodate ion, would be twice that, or 6.6 times 10 to the negative 3 molar. So remember, what you're saying when you finish solving this is that that many moles per liter of solid copper 2 iodate dissolves to give you the same number of moles of copper 2 plus ions and twice the molarity of the iodate ion. You can qualitatively compare Ksp values if the number of particles produced are the same. The common ion effect will always shift the reaction to the left. Based on Le Chatelier, it's always going to reduce the dissociation and the solubility. So calculate the solubility of a silver sulfate in 1 molar sodium sulfate. Set your problem up. Include the molarity of the sulfate ion that's coming from the silver sulfate. That gives you 2x, and then 1 minus x for your sulfate ion. Putting it into the expression, for all your Ksps, you'll be able to throw that x out and simplify. So your Ksp expression, throwing that x out and simplifying, gives you an x of 1.9 times 10 to the negative 3 moles per liter that dissolves in 1 molar solution. If you had found the amount that dissolved without the common ion, you would find that it would be more. For a hydroxide, they may give you the pH. So all you have to do is turn the pH into the hydroxide. So turn the pH into the POH, and then the antilog of that will give you the concentration of the hydroxide ion, and then set up your equilibrium expression. You will easily be able to throw out that 3x in the expression at the bottom to simplify the algebra. Solve for x. Well, a precipitate form is simply a matter of comparing Q and K. So if Q is greater than Ksp, the reaction is going to form a precipitate. If it's less, you will not get a precipitate, and if it's equal, you're in a saturated solution. So you can't make silver nitrate solutions in tap water because the chloride ion will be enough to start the precipitation of silver chloride. To determine if a precipitate will form, you take all the numbers in the problem, and all you really have to do is figure out the molarity of each ion and put it in the expression and compare Q and K. So here we've written the expression, we've got the Ksp value. Find the silver ion concentration. We use the 1-to-1 mole ratio between the silver ion and silver nitrate. To find the chromate ion, we've got to turn milligrams to grams to moles, and finally to moles per liter. And then put the molarities into the Ksp expression and solve. Q in this problem is less than Ksp, so no precipitate will form. In this problem, are we going to get a precipitate? Solve for the moles of each. Now notice you've got to make sure that that final molarity is the total volume. So you've got the moles of MgCl over the total volume and the moles of NaF over the total volume. put it into the Ksp expression, and this time Q is greater than Ksp, so a precipitate will form. Going through this problem, again, the lead ion's concentration, the iodide ion's concentration, put them into the expression, and yes, you will get a precipitate. So these problems are tedious, but they're really pretty straightforward. Get the molarity of each ion and put it into the expression. pH can affect solubility, especially if you have hydroxides, your magnesium hydroxides or your transition metal hydroxides are pretty insoluble. So you can remove that hydroxide ion by increasing the hydronium ion. This is pretty much Le Chatelier. And then how much do you need to add to get a precipitate? This is the last type of calculation. They are going to give you information about the ions, and then they're going to add an ion, and you have to decide how much you need to add to first get a precipitate. So if you look at the problem, it looks confusing, but if you write out the Ksp expression, you can see that you have the Ksp and you have the molarity of one of the ions. So all you're doing is finding the missing ion and how much you're going to need to get a precipitate. When you get that ion, any in excess of that will cause the lead to iodide to precipitate. So you found the iodide ion. You do the same thing to find the iodide ion and how much you'll need to precipitate the copper to iodide. And then you compare those, and whichever one has the least amount that it needs to form the precipitate will be the one that precipitates first. So Ksp problems, there are only a few types. They're pretty straightforward, not much theory, a little bit of math and algebra.